Hi, and welcome back to the Vex Classroom. Okay, you're probably very excited right now because you're getting ready to compete with your robot against your peers in our STEM game in our classroom competition. Now, before you actually jump into the competition itself, this video we're going to talk about the engineering design process and how you can actually apply it to your strategy in the competition to hopefully put you in the best position to win. So this video is actually going to talk about two things. Number one, what the engineering design process actually is. And then number two, how you can apply it to what you're doing with your team right now in the competition to, again, come up with the best way to compete and hopefully win in your STEM game within your classroom competition. So first, let's talk about the engineering design process itself. Engineering, when I talk about engineering, what does that actually mean, that word engineer? And at the end of the day, engineering is all about problem solving. The famous saying goes that scientists investigate, engineers create. And what engineers oftentimes create are solutions to real world problems. That's what engineers do. Engineers are problem solvers. With us in the competition, our problem is we want to win. We want to get the highest score that we possibly can. So that's the problem that we are trying to solve. Now, design. What does design mean in this context? Well, a design is something that is systematic. It is a methodology or a process, as you see here, that you are applying to that problem solving. Essentially, what that means is you do not just want to guess and check your way to an answer. You don't want to just try things and kind of see what works and muddle through that process. Instead, you want a systematic way to test, evaluate, and hopefully use data to make your decisions. All of that is encompassed within the engineering design process, which I'm going to talk about right now. So what you want to think about is how you're going to apply this to the competition, to your team, because if you apply this to your competition and to your team, you're going to do very well. Successful teams that have gone on to the Vex Robotics World Championships, teams that are very successful, they have some type of process that they undergo and that they apply when it comes time for them to compete. Again, they're not just trying to guess and check their way to get a solution or try to get the highest score that they possibly can. So let's go ahead and take a look now at the engineering design process as it's applied to what is that we're doing in robotics competition. Now, if this looks familiar to you, that's because we are using the same engineering design process that is found in the next generation science standards, specifically the define, develop solutions, and optimize sections of the engineering design process. You'll notice, first of all, that this is very cyclical in nature. So this is not something that you're going to do in a linear fashion. You can skip around. You can do the optimize first, then you can define, then you can develop a solution. You don't have to go in this process, but most importantly, you're going to go through this process many different times. The great things about classroom competition, the STEM games, and the actual Vex Robotics competitions is that you always have the opportunity to improve. You're never, quote unquote, done. You can always try one more thing to try to optimize your solution, score a little bit higher, make your robot that much better. So you never have that situation in class where you're going to get done before the rest of your classmates. Instead, you should constantly be trying and iterating, and don't worry about trying something new and kind of mess up what you already have. We're going to talk about how you can prevent that from happening by applying the engineering design process. So let's take a look at it and talk about how you would actually apply this in a STEM game classroom competition setting. The first step, define, is you want to understand the scoring and you want to understand the game rules. And we have a video here in this section that goes through all of that for you. It's very important that you understand how to score, and it's also very important that you understand the game rules. That's really the first step in any competition, or honestly, any sport. If you're playing football, basketball, baseball, no matter what it is, you have to understand scoring and you have to understand the rules. After that, then you're going to think about how the scoring and the rules impacts the design of the robot itself. So what are you going to do with the design of your robot in the individual STEM Lab units that you've had before this particular lesson on the competition? You might have talked about different engineering concepts, and you want to think about that in the design of your robot. And then the last part is the game strategy. Game strategy is talking about the scoring itself, not just how is your robot going to get the highest possible score, but how can you also prevent your opponent from scoring. That's the game strategy. Game strategy you can also think about if you're using a controller, who's the best driver on your team. Those types of things all go into the game strategy. And one thing I should have mentioned when I talked about robot strategy, your robot design, is if your STEM Lab unit that you're currently in is very coding focused, that also thinks about your actual code itself, the project that you're making. It's not just the actual engineer of the robot, but the code that you're going to be using in the robot. All of that you're going to want to document in the engineering notebook. That's the last step in the define stage. This is really kind of the first step or the first prototype that you're going to use. Now, you should not be starting from scratch because, again, you've had previous lessons in this unit that you've used to develop and learn things about this competition. Because of those previous lessons, you should essentially have a prototype, the prototype code, the prototype design of the robot, an idea of how you're going to score the actual game strategy itself that you can now apply. And that goes into the second part of the developed solutions. Now you want to test. You want to see how your initial prototype, what you've built based upon the previous lessons in the STEM Lab unit, how it actually does. You can test it amongst yourself, and then you can compete in the actual competition itself. Now, very important for you to understand is in these classroom competitions, you are not just going to compete once. You're going to compete numerous times. Teams in VEX robotics competitions that go to a lot of different competitions oftentimes perform well, and they make a lot of improvements with their robot from that first competition to their third, fourth, or fifth competition. That's because they learn through that testing process, and they also have the opportunity to see other robots and what those other robots have and how they can apply that to their own robot design. So very important that you test and compete, and that gets into the evaluate and the observe portion, the things that I just talked about. When you go in and you test and you compete and you don't get the highest score that you possibly thought that you could get, why is that? Be analytical about that. Don't just be upset that you lost the game, but instead actually evaluate how your robot did. Compare that to the rules and to the scoring, and then use that to do in the next step to optimize your actual design. And then observe, what are the other people doing? You could have one person on your team that's just in charge of scouting, and they can actually go and watch other matches and see what other robots in your classroom are doing, and then see how you can apply those concepts to your own robot design. So observation is very, very important. We do this in all different walks of life. If you're a software engineer and you're beginning to write code, you're probably going to use someone else's library of code, someone else's API, and apply that to what it is that you are doing. If you're building a house or you're building a bridge, you're probably getting inspiration off what other people did. So there's nothing wrong with observing what other people do, see what they did well, and applying it to what it is that you're doing with your particular robot. Unfortunately, people can sometimes think that's quote unquote cheating. It's not. You're actually observing what other people are doing and applying it to your own robot. That's a very important step in the engineering design process because you're evaluating, like we talked about, and all of that is taken into consideration, that first step, that define step, when you're thinking about the scoring and you're thinking about the rules, you're thinking about the robot design. So there's a lot of thinking going on here. It's just simply not a matter of copying what someone else is doing. You're actually doing a lot of thinking and applying that thinking to what you want to do with your robot in the competition itself. So again, you're going to document all this in your engineering notebook. If you are a scout, you can document what other people are doing with their robots and have that discussion with your team. You can document what's going on during the test. You can document what's going on when you actually compete. You can write down the evaluations, what you think your robot did well, or what you think your code did well, what you thought the robot did not do well, and what you thought the code did not do well. You can document all of that and decide what it is that you think you might want to do, and then that takes you into the optimize step. You can take a look at the engineering, the mechanisms of your robot, the actual robot design itself. That could include code, your game strategy, and the rules. Now, the important thing about the first thing, about the mechanism, the robot design, and the game strategy, with each of those, you just want to change one thing. You don't want to totally overhaul your robot. You don't want to make a ton of changes, because then when you get back to the define step and you think about what is that you're doing and you go back and you test again, it's impossible for you to make an informed judgment on what worked and what didn't work if you have too many variables. So you want to change one thing about your robot design. Maybe just manipulate the gear train robot. Change one thing on your code. Change one thing. Document that one change in your engineering notebook, and then you can kind of, if you want to go ahead, as I talked about, this is not linear. So after you make that change and you optimize, if you want to go back to the develop solutions part and test, that's why this arrow here goes both ways. You can go ahead and do that and evaluate if that experiment that you just ran, if it worked or if it didn't work. And maybe you want to run that test a few times so that you have a nice body of evidence to make a good decision if that test worked or if it didn't work. Now, during this portion, when you're defining what you're going to change and you test and you evaluate, this is where communication is so very important. That's why we have a video on collaborative decision making, because getting everyone on the same page can sometimes be a little bit difficult. That's why we have that video on collaborative decision making, which is also on this page. Go ahead and check that out. And that's going to help you and your team decide upon that one thing that you're going to change, evaluate if it worked or if it didn't work. You can all be on the same page with that. But it's very important that you actually communicate all those things. And then you can document everything again in your engineering notebook, like it says right there. Now, it's very important we talk about this documentation step. It is in all three of our steps there. The documentation, though, it's not just a recording of facts. You're doing that, but that's not just what it is. It allows you data to make an informed decision. Let's say that you missed class for a couple days. Now you can come back in and see what your teammates did and help them make an informed decision as a result. It's impossible for us to keep everything in our heads at all times. We can write and we can document the results down. That way, again, we are making decisions based upon data. So your engineering notebook is not just an artifact. Instead, it is something that you're going to interact with throughout this entire process. It's going to help you make decisions. It's going to help you learn. It's going to help you, yes, keep track of things, but it's a very interactive document in that it's not just a receptive one. Instead, you are going to use it to help communicate with that collaborative decision making like I talked about. And it's also going to help you communicate decisions that you're going to make and why you should make those decisions. And to go back to something that I said before, if you do try to run an experiment with your robot and it fails and it doesn't go well, you can always reference back to your engineering notebook, the design of your robot previously, and go back to that. So you should never be in a position where you're worried about changing something on your robot and you essentially have to start back from zero or start from scratch. Instead, the engineering notebook allows you to change one thing, and if that one thing you change doesn't work, go back to your previous design because it's documented, and then you can decide if you want to change one thing again or not. So it takes away the risk of changing something on your robot or changing something on your code that could make you go back multiple steps or go back to zero essentially. Instead, the engineering notebook tracks all of that, and it allows you to make informed decisions, but it also allows you to go back to previous iterations so you know you at least have that base that you're always going to be starting from. So the engineering design process is something that's used in the real world by actual engineers every single day to solve problems that we're faced with, STEM problems that we're faced with all around the world. And it's something that you can also apply to the context of the robotics competition here. And we've taken the engineering design process from the next generation science standards and applied it to what we're talking about here with our STEM games and with our classroom competitions. So not only are you actually solving problems, right, getting the highest score you possibly can, and you're doing it in a systematic way, but you're also modeling something that you could potentially be doing if you pursue a career in engineering, or potentially be doing with any type of career, even if you're not an engineer, if you have to solve problems. Being able to solve problems in a systematic way, be able to communicate that, be able to make decisions, those are such important things and such sought after things for our 21st century knowledge-based economy. You're getting great practice in that right now in our STEM games and with our classroom competitions. A couple of tips to kind of sum this video up here. Number one, don't do too much. Always keep in mind when you get to that stage where you want to try one thing and you want to change one thing, keep in mind what your team can actually do. Don't let your eyes get bigger than your stomach. Don't try something that's kind of outside the talent that your team has, what you could possibly do. Additional to that, you might be able to do it, but if it takes you 2 weeks to do it, that's probably not the best idea to be able to do. Keep it simple, try small things. It's an accumulation of those small things that are eventually going to allow you to have big changes. Or find the most high leverage thing that you can change either with your code or on the robot itself. And what I mean by high leverage is what's the smallest possible change you can make that could potentially have the largest impact. That's a much better strategy than trying to do 3 or 4 bold things that your team might not have the time to do or might not have the ability to do. So keep that in mind as you're working through the engineering design process. Secondly, don't be afraid to ask for help. Always ask for help. Ask your teacher for help. Don't be afraid to ask your classmates for help. Ask another teacher for help. Don't be afraid to do that as you're going through the engineering design process. The engineering design process is not just collaborative amongst you and your team, but it can also be collaborative with your teacher and other teachers, your parents. Get as many different people involved, get as many different ideas involved as you are using the engineering design process. It's going to make it that much more impactful for you. Also, keep in mind the collaborative decision making. It's a very good idea to be collaborative. More ideas is always better than one idea, so keep that in mind as you are working through the engineering design process. Again, the whole purpose of this is if you apply the engineering design process, you are going to do very well in the game. Remember, it's cyclical, so you're going to do it many different times. You do not have to do it in a linear fashion. You can optimize something and then go back and test it again, so don't worry about that so much. But becoming accustomed to the engineering design process and applying it to solving problems is a terrific skill, not only to have fun in the STEM games, but can also be applied to many different real-world applications. So go ahead and apply it. Have fun competing, and I can't wait to see how you're going to apply the engineering design process.